Imagine a simple metal box costing a mere $150, equipped with just a fan and a small water pump. It can drop a room's temperature by 30 degrees Fahrenheit without compressors, refrigerants, or complex chemical cycles. Just water evaporating across a wet pad. The same natural principle that cools your body when you sweat. Meanwhile, a central air conditioner performing the identical cooling task in the same room consumes 14 times more electricity. Installing one sets you back $5,000 and demands replacement every 15 years. Yet for decades, homes in the American desert relied on this humble, affordable solution, only to abandon it in favor of the pricier, profit-driven alternative. Today, the inexpensive evaporative cooler sits quietly on store shelves, largely unknown to anyone under 40. This approach isn't new. Ancient civilizations understood it intuitively. Around 2500 BC, Egyptians had servants wave air across clay vessels brimming with water, cooling their spaces as heat transferred into the liquid. In Persia, wind towers directed scorching air through subterranean channels, passing over water to reduce temperatures by 20 or 30 degrees before reaching living quarters. In India, damp grass mats, called ku curtains, were hung across doorways to bring relief. Each society facing severe heat independently discovered the same solution. Evaporation pulls heat from the air. This isn't speculation. It's a phenomenon proven by millennia of practical use. Modern evaporative coolers operate on the same straightforward principle. Hot air from outside is drawn through pads soaked in water. As the air moves through, the water transforms into vapor, extracting heat in the process. The Department of Energy estimates such systems can reduce temperatures by 15 to 40 degrees Fahrenheit, depending on climate conditions. No refrigerants, no chemical cycles, just a fan, a modest pump, water circulating over absorbent pads, and the laws of physics. Remarkably, the air introduced into the home is not recycled. Fresh outside air enters continuously, cooled by evaporation, requiring windows to remain slightly open to allow airflow. The entire indoor air volume cycles every few minutes. In contrast, central air conditioning seals homes briculitis, circulating the same conditioned air through filters repeatedly, often leaving occupants feeling dry, stale, and fatigued. The swamp cooler, however, breathes life into the space instead of locking it in a closed loop. Its efficiency shines in arid climates, but falters where humidity runs high. Evaporation demands capacity. In dry air, water vaporizes quickly, extracting substantial heat. When moisture saturates the air, evaporation slows and cooling power diminishes. This limitation, not the technology itself, dictates performance. Yet the numbers are striking. A study by the University of Arizona examined a 2,000 square foot home in Tucson during summer. The evaporative cooler consumed 250 kilowatt hours per month, whereas a central air conditioner required 850. That's 70% less electricity. Comparing wattage paints an even starker picture. The cooler draws about 250 watts, while a compressor-based system pulls 3,500 watts, 1/14th, the power for comparable comfort. On a utility bill, the difference is stark. Running the cooler for a full summer costs roughly $150, with an additional $54 for water. In contrast, the air conditioner racks up $600. Over the summer, the cost gap can exceed $400, recurring every year. Installation costs follow a similar trend. Central air ranges from $3,800 to $7,500, while whole house evaporative systems, typically rooftop mounted, run between $500 and $1,500. Even window-mounted units, sufficient for individual rooms, cost only $150 to $400 and plug into standard outlets. No HVAC licenses, no permits, no refrigerant lines snaking through walls. These findings are not fringe claims. The Department of Energy confirms that evaporative coolers require roughly a quarter of the electricity of conventional air conditioning and cost about half as much to install. What's astonishing is that this isn't new technology. Entire regions of the American Southwest once built their lives around it, only to abandon it over time. Oscar Palmer, in Phoenix, Arizona, introduced the first commercial evaporative cooler in 1908. Within 25 years, thousands of homemade variants emerged, wet burlap stretched over window frames, damp sheets hung in front of fans, all harnessing the same ancient, effective principle. This is a legacy of practical ingenuity, quietly waiting to be rediscovered. By 1939, nearly every home and business across the southwestern United States relied on some type of evaporative cooling. Phoenix alone, by 1940, hosted over 30 companies producing these units. The city proudly dubbed itself the air conditioning capital of the world. Not compressors, not mechanical refrigeration, but the original kind. For decades, this was sufficient. It transformed life in the desert into something bearable for ordinary families, all at a price they could manage. Then, Willis Carrier's mechanical air conditioning caught up. Carrier had patented refrigerant-based cooling back in 1902, yet for 50 years it mainly served commercial spaces, movie theaters, department stores, factories. Residential window units did not appear until the late 1940s. Central air for homes emerged in the mid-1950s, and even then, adoption was gradual. By 1960, only 1 in 4 Phoenix households had installed refrigerated air. The majority, 3 out of 4, still depended on evaporative coolers. 2 significant events converged to change that. In 1965, a construction strike in Phoenix froze new home development. Builders shifted focus to retrofitting existing houses, and the most popular modification was removing swamp coolers in favor of refrigerated air. Simultaneously, post-war cheap electricity, GI Bill financing, and the suburban construction boom created a housing model centered on ductwork and compressors. Developers mass-producing tract homes installed central air, not swamp coolers. It was more expensive, consumed more electricity, but could be produced, financed, serviced, and built month after month for the lifespan of the house. By 1980, the swamp cooler had gone from standard to obsolete. Today, only around 7% of Phoenix homes still operate one. The rest endure 4 times the energy cost to achieve the same comfort in the same climate. The numbers alone are staggering, but the story worsens with the name. Early evaporative coolers used aspenwood fiber pads that rotted if not cleaned, creating algae in the water reservoir. Bugs and mold could move in, leaving the entire system smelling like a swamp. The nickname swamp cooler stuck. Imagine trying to sell that to a homeowner when the alternative is called air conditioning. One evokes comfort and convenience. The other, decay under the porch. That single label harmed the technology more than any competitor could have. It is important to be clear, evaporative coolers do not function everywhere. This is not a side note. It is the core reality of the technology. Ignoring it would be misleading. In deep desert midsummer conditions, like Phoenix with 10% humidity, a cooler can drop indoor temperatures 25 to 30 degrees Fahrenheit. At 20% humidity, expect 20 to 25 degrees. At 40% humidity, roughly 15 degrees, still significant and still far cheaper than conventional air conditioning. But once humidity surpasses 50%, cooling efficiency diminishes sharply. Above 60%, the effect is minimal. In humid regions, such as Houston, Miami, or Atlanta, where summer humidity often ranges from 60 to 80%, this box cannot cool effectively. It only adds moisture to the air. This is straightforward physics, and the honest explanation for why much of America adopted refrigerant-based systems. Yet this context leaves out a key point. Western and mountain states, Arizona, New Mexico, Nevada, Utah, Colorado, California's Central Valley, West Texas, and parts of Montana and Wyoming sit perfectly within the climate range this technology was designed for. Tens of millions live there, yet most pay $600 a summer to run a compressor when a simple box could deliver the same cooling for $24. Not because the cooler fails, but because the surrounding system evolved. There was no conspiracy. Evaporative coolers remain available on store shelves today, online orders tonight, and recommended by the Department of Energy. This is neither banned nor hidden. What occurred is simpler, yet harder to reverse. The entire HVAC ecosystem, contractors, supply chains, building codes, reorganized around the compressor. The U.S. HVAC market generates over $30 billion annually. 88% of American homes now have air conditioning. Contractor certifications focus on refrigerant handling. Financing revolves around installations costing $5,000 to $15,000. Swamp coolers have no service contracts. There is no refrigerant to recharge. No annual tune-up producing a $200 invoice. Pad replacements cost around $20, swapped once per season by the homeowner. Pumps, if they fail, are $30. End of summer maintenance is draining the water, wiping the housing, and letting it dry for 20 minutes in the driveway. Think about a spring visit from an air conditioning technician, $150 to $300 just to inspect refrigerant levels and hose off the condenser. Now compare that to a simple box costing $150 that removes the need for a $5,000 installation. There is no conspiracy here. It is simple arithmetic, something no one in the supply chain has motivation to solve for you. Yet the air conditioning industry pulled a quiet sleight of hand few discuss. They redefined a word. Originally, air conditioning referred to any system that conditioned air. Heating, cooling, filtering, or humidifying it. In the American Southwest, evaporative systems were the standard. That is what the phrase meant. Over time, the refrigerant industry co-opted the term, making it synonymous with compressors, sealed units, and $5,000 price tags. The swamp cooler was linguistically evicted from its own category. No grand plot, just the inevitable result when one side wields marketing budgets, while the other offers a metal box with wet pads. So what does actually buying one look like today? A portable, evaporative cooler, the type you roll from room to room, cost between $100 and $250. Fill the reservoir, plug it into a wall outlet, and direct airflow where it is needed. Operating expenses hover around $20 to $30 per month. No installation, no permits, no technician visits. Window-mounted units that cool a full room or part of a house range from $150 to $400. They install like a standard window AC unit, but are lighter, simpler, and contain no refrigerant lines. You can attach a garden hose for continuous water or fill the reservoir manually. These machines move serious air, 3,000 to 5,000 cubic feet per minute. Crack a window across the room to give it an escape path, and the entire space cycles fresh, cooled air every few minutes. For full house cooling, rooftop-mounted systems ducted through the ceiling run between $500 and $1,500 installed. This is exactly the setup that kept Phoenix homes comfortable for 40 years. It remains available. It still works. And it costs a fraction of central air. In climates with alternating dry and humid periods, you do not have to choose. Use the evaporative cooler during dry months when its efficiency and electricity savings are at their peak. Switch to traditional AC when the monsoon arrives, or humidity climbs above 50%. Some Arizona homes have run both systems for decades. The cooler handles the extended dry stretches, the AC tackles humid weeks. Annual cooling bills drop roughly 50% compared to using AC alone. This is not a workaround. It is the intelligent method for cooling homes in mixed climates. Yet almost nobody sets it up this way because the HVAC industry does not profit from recommending it. Imagine turning it on for the first time on a sweltering June afternoon. Outside, it is 103 degrees Fahrenheit, air-bone dry. The fan whirs, the pump circulates water over the pads, and within minutes, the air blowing into the room feels distinctly cool against your hand. Not the hard, dry chill of conventional air conditioning, but something softer, reminiscent of standing beside a lake with a gentle breeze off the water. The scent is faintly clean, not recycled, not forced through the same ducts for the 10th time today. Fresh air flows while your electricity meter barely ticks. No compressor cycles, no condenser dumping heat into your backyard. Just water performing its age-old function, absorbing heat from the air as it evaporates. Here is what keeps drawing me back. The regions heating fastest are the very ones this technology was designed for. Western states, desert regions, where humidity is low and electricity demand spikes every summer. The Department of Energy projects global cooling demand to triple by 2050. And the solution most reach for, the compressor, the refrigerant, the sealed system, is the very one that consumes the most electricity and produces the most waste heat. Every AC unit in Phoenix expels heat back into the outside air, making the city hotter and forcing the next unit to work harder. It creates a feedback loop that intensifies as adoption increases. Evaporative coolers, on the other hand, do not expel heat. They absorb it. The energy goes into converting water from liquid to vapor. It does not return through the wall. Meanwhile, refrigerants in AC systems, hydrofluorocarbons, leak over time and act as greenhouse gases hundreds of times more potent than carbon dioxide. The working fluid in a swamp cooler is water. One system worsens the problem it seeks to solve. The other does not. Over 118 years ago, a man in Phoenix built a simple box with wet pads and a fan, and it made life in the desert bearable. That technology remains on the shelf today. The physics has not shifted. The price barely changed. What has shifted is our definition of air conditioning and who profits from that definition. Thanks for watching. See you in the next one.